Okay, we have a pretty tricky integral today from MIT Integration Bee 2023, finals number 3. We have the integral from minus a half to a half of square root x squared plus 1 plus square root x to the fourth plus x squared plus 1 dx. Okay, so this one is not easy. I was thinking about how someone would do this with a 4-minute time limit. I myself got the problem wrong like 10 times before I got it right because there's so many little places to make minor mistakes. I had trouble with the end part of just getting the calculation right. But anyway, to get started with it, there is a nice way to simplify this thing right here. This is actually a lot like a problem you'll see a lot like on YouTube and sometimes in life where you have something like square root of 8 plus 2 square root of 15. A lot of the examples might be more complicated than this, but it's still the same idea. For this is actually the same thing as square root of 5 plus square root of 3. Now in our problem, what we have here, this is not a number, but we can still use this same principle. The way we do problems like this is what you want is you want the stuff inside the square root to be a perfect square. Now there's no guarantee that it's going to be nice, but if it wasn't nice, then the problem might become kind of impossible. So I'm going to kind of assume that what's in here can be written as a perfect square. So then the way to look at these problems in reverse is if we assume everything inside the radical is something in this form, square root of a, square root of b, all squared. Just because if this is in a square root, we're going to get back square root of a plus square root of b. Now, if this was a minus sign, you might have to worry about absolute value, but it's not a concern for us where we're adding two positive values. And so then what I can do is, let's see what happens if we just square this out. So when you square the square root of a, you're going to have an a. And then here, this is going to become plus b. And then you multiply out the middle terms, and you're going to get 2 square root of ab. Then what we can do with this is equating it back to what we have here. Just kind of match up. Like, here's our radical. So we're saying we want this piece here to be ab, and we want this piece here to be a plus b. But there's one problem with what I'm doing here. Notice we don't have this 2. So in order to get it to match this formula completely, we can just create that. If I multiply by square root of 2, then we can distribute that in here. But I don't want to change it, so we'll multiply by 1, square root of 2 in front. So now when I distribute that 2, and let's just look at the radical before we even think about the integral. So if I basically just distributing a 2 to every term, so it's going to become 2x squared plus 2, and now we have the 2 in front here, 2 square root x to the fourth plus x squared plus 1. And so now that we've created this 2 here, we've got a way to match this up. We're saying we want this piece right here to be a plus b, and so we want this piece, sorry, this is x to the fourth. We need this piece to be a times b. So what we have here is a system of 2 equations, 2 unknowns. We could do it out formally, but I'll kind of do it on the fly, kind of more guess and check. You know, you could, for 2x squared plus 2, one thing that looks like it would work, just looking at this part, would be like x squared plus 1 plus x squared plus 1. So then we'd be saying that this is going to be a and this is going to be b. And so if you multiply those together to get an a times b value, we're going to have, just distributing this out, x to the fourth plus 2x squared plus 1. Not quite a match. We've got this 2 here, so it almost looks like this, but there's a little problem. We've got this 2 here. Well, it turns out there's another way to do this really similar. What I can do is, for a plus b, what if I did x squared plus 1 plus x, and then for the other one, x squared plus 1 minus x. So that way these x terms that I just tacked on, those are going to cancel out, and we still get 2x squared plus 2. And then if we do out our a plus b value, you can think of this now like a difference of 2 squares, kind of like if I create parentheses around it, like I think I have the right amount of parentheses. Now squaring the first term, we get the same thing we had before, x to the fourth, 2x squared plus 1. And then we need to square the last part minus x squared. But when you simplify that, 2x squared minus x squared gives me x squared plus a 1. And this is the same thing we have right here. So what we have here, this is our a again, this is our b, and what we're saying is we have it now in this form, which is the same thing as this right here, a perfect square. And so what we can do is transform all of this stuff to this form of just square root of a plus square root of b. If any of this algebra is unfamiliar, I did a whole video on all the different scenarios for this. There was like 5 or 6 different problems with variations on this. So I'll provide a link to that. It was a few months back, but it kind of covers all this in greater detail. Okay, so now I have this rewritten just from what we found on the previous board. We're using this square root of a plus square root of b that we found. And so we have this. But now, even after we reduced it, it's still not really a trivial integral. We still have some work to do on this. That's kind of what I thought was interesting, is in a lot of the problems in integration bees, if you solve the one trick, then you're kind of done, you're home free. But here we still have to work out this thing, and actually it's kind of 2 integrals, right? Even though they're both really similar. Now, one thing I can do on this that I should have done before is notice, not really looking at this one, but you can tell here that this is an even function because everything is squared and our bounds are symmetric around 0. So I can use that principle for an even function with symmetric bounds. We can turn the lower bound to a 0 and then just bring a 2 out front. And so I'll bring that down here as well. Now going ahead with this integral, first what I want to do is complete the square. And I'm going to work these in parallel because they're both so similar that we're just going to kind of do this side by side. So for completing the square on this, if you look at this as a 1 exponent, just take half of it and square that. Now, if you square out this thing, you get x squared plus a half as the plus x plus a fourth. To get to the plus 1, we have this as 3/4. But what I really want to do is write this as something squared. So I can write this as square root of 3 over 2. And then just notice I can do the exact same thing over here, just with a minus sign. So this one's going to become x minus a half, square it, same thing happens, and we'll write it this way, square root of 3 over 2, all squared. And then from here, what I want to do is a trig substitution on it, but I actually want to do the hyperbolic trig substitution. I mentioned before that I got the wrong answer like 10 times. It's actually fine to do it this way, but you could substitute here and call this tan of t for like a normal trig substitution. There's nothing wrong with it, but I just found it a little more messy for myself. Maybe just personal preference, but I kept getting the wrong answer doing it that way, just making silly mistakes with the derivatives and stuff. So instead what I'm going to do is make the substitution for this for sine of t, but I want this square root of 3 over 2 in front of it to make it simplify nice. So what we'll do for the substitution is I'm going to say x plus 1/2 equals square root of 3 sine t. Then do it in parallel over here. X minus a half is going to be square root of 3 over 2. We'll use a different variable. We'll call this one sine of u. Sorry, I meant to do a hyperbolic trig substitution, not the regular for sine. So this is supposed to be sinh of t. And over here, we're going to have sinh of u. This comes in handy a lot just because the derivative's nice and it just seems to simplify. In some cases, it simplifies nicer. So taking the derivative, we're going to have dx square root of 3 over 2. Derivative of sinh is going to be cosh t dt. Same thing over here, we get dx square root of 3 over 2 cosh of u du. And then on both these, I want to solve for t and u to isolate it so we can update everything. So let's just do that by multiplying by 2 square root of 3 on both sides and then taking the inverse. Okay, so now I'll go ahead and substitute. I'm going to break it into 2 integrals. One thing I can do, 2 over square root of 2, this is the same thing as square root of 2. You can just rationalize it and it'll simplify that way. So we have square root of 2 in front. Now updating the bounds, you plug a half in here. 2 times half is 1. You're going to have 2 over square root of 3 here. I'm not going to simplify it. I'm just going to leave this as sinh inverse 2 square root of 3. Plug a 0 in here. This one's going to become sinh inverse 1 over square root of 3. Now when we do the substitution, I'm going to use this version here instead of what we have in the square root. Just kind of plug that back into the square root and substitute on this. So what's going to happen here, we're going to have square root, we'll put it back as 3/4 for now, I don't know. So squaring this, we have sinh squared t, and then this becomes, we'll put this back as 3/4 for now. And then for the dx value, it's going to become square root of 3 over 2 cosh t dt. And the second one's going to work basically the same thing. We get the square root of 2 in front. Now we're plugging in, if we plug a half in here, notice this now, the angle becomes 0. Inverse sinh at 0 is just 0. Then you plug a 0 in, and then this is going to become inverse sinh of minus 1 over square root of 3. And then for the rest of it, it's going to be basically the same thing as what we have here. So let me just copy all that down. And now at this point, it looks like we've made everything worse, but we're going to be able to simplify this pretty nicely. But let me just clean up the board and we'll deal with these 2 integrals. Okay, so now let's focus on simplifying this whole mess. It would be nice, there are some formulas that might be able to shorten some of this, but I don't really remember those formulas, and I also want to show how it works, so we'll just keep going. So one thing I did is I pulled the square root of 2 in front because we had that on both these. And next what I can do, so square root of 3 over 2, this is a constant. We'll do these again in parallel because it's going to be the same in both cases. But also from here and here, we can factor out 3/4 inside the square root, and that's going to be another square root of 3 over 2. So if I pull this out in both cases, we'll pull it all the way in front. This is just going to be multiplying it together. It's going to be 3 over 4. So then we'll get rid of this, get rid of this. But then here we have got this identity, sin squared plus 1 is the same thing as cos squared t, or over here it's the same thing as cos squared u. But we're inside the square root, so it's just going to become cos of t. When you multiply it times cos of t, then this whole thing, this just reduces down for the whole expression, the cos squared t. But then I'll use the power reduction on this. This is going to be the same thing as 1/2 times 1 plus cos of 2t. And then what I can do is rewrite both these integrals just like this, but take the 1/2 and I can factor it out front. But now bringing the 1/2 out front, this 4 became an 8. And then here, now the integrals are really easy. We can just kind of do these integrals and it's just going to be a matter of evaluating it. So the antiderivative for this thing, it's just going to be, here it'll be u plus sinh 2u, and we have a 1/2 come out. But before I rewrite everything, sinh 2t, we've got the same double angle formula we have just for sine of 2t. This is the same thing as 2 sinh t cos t. And then we have this 2 plus, we have the 1/2 in front, but 1/2 times 2, that's just going to be a 1. Now, one thing I want to do before we evaluate, just notice we've got the crazy bounds going on with inverse sinh, not reduced. Well, in order to help with that, I'd like to get everything in terms of sinh. I don't really want the cos term here. Well, what I can do for that is use this identity that cos squared u minus sinh squared u equals 1. So if you just rearrange this and solve for cos, you get the equation that we used earlier when we did the initial trig substitution, which is just we can have cos u as sinh squared u plus 1. No need for absolute value or plus minus signs. Cos is always positive, so we can just use this right here. And so when we integrate this, let's write it this way. We'll have 2 plus, this is just going to be sinh of t. And then for cos t, we'll just use this thing, sinh squared t plus 1. And now that we have each of our integrals reduced like this, we'll just take these, plug it back in, and we just need to evaluate these at these bounds. Okay, now finally we're ready to evaluate this thing. First, let's deal with the easy part, 0. You plug a 0 in there, that's 0. Sinh at 0 is also 0. This part doesn't matter because we're multiplying by 0. So what's going to happen is we can just ignore this because everything's 0. Now, one thing I want to do with this bound here, sinh is an odd function and inverse sinh is also an odd function. So we've got that minus sign in front. I could just take that all the way out front here and I can write it as minus inverse sinh 1 over square root of 3. That way what's going to happen, this piece here is the same thing as this. So let me just move that minus sign right there. So now what I want to do is just evaluate this part and this part together just because I want to get some cancellation. And because we're evaluating the lower bound, there's going to be a minus sign that's going to come in front of it. So first plugging into the t here, this is going to be minus inverse sinh 1 over square root of 3. This one minus sinh of inverse sinh just is going to become 1 over square root of 3. This one, same kind of thing, it's going to be 1 over square root of 3. You square it, you get 1/3 plus 1 here. Over to this one, again, we're going to have a minus sign for everything because it's the lower bound. So we have minus, plug this in, and we're going to have we're just going to have this whole thing minus inverse sinh 1 over square root of 3. Same thing over here. Again, sinh is an odd function, so this minus sign I can bring out front, and then sinh of the rest of it is going to be 1 over square root of 3. And then inside, the minus sign is going to get squared out this time, so it's going to be 1/3 plus 1. Same thing we had over here, square root of 4 over 3. But then I can distribute the minus sign in here and make everything plus. But then just notice this one's going to cancel with this one and give 0. This one is the same thing as this, just subtracting. This is going to cancel with this and give 0. So all this stuff becomes a 0. This evaluation and this evaluation goes away. And we just need to evaluate this here. Forget about this. So finally, let's get to this part. We still have our 3 square root of 2 over 8 in front. Then just plug in here. We'll just leave this for the moment. So this is just going to be sinh inverse 2 over square root of 3. You plug this in here, we get plus we get sinh of inverse sinh. We're going to have 2 over square root of 3. Inside, same kind of thing, but then we square it and we get 4 over 3 plus 1. Now for this piece here, we can get a common denominator, write it as 4 over 3, make a 1 into 3 over 3, put this together, and it's going to be, we'll separate it out and we'll write it as square root of 7 over square root of 3. Now for this, we could actually leave it, but I want to get it to look like MIT's solution, so I'm going to put this in the form of the natural log. The formula for that, if you have inverse sinh of x, that's going to be the same thing as natural log of x plus square root x squared plus 1. So then for what we have here, for sinh inverse 2 over square root of 3, just using this, we're going to have natural log 2 over square root of 3 plus square it. Then this is going to become 4 over 3, but then it's going to be the same thing as this. This actually is going to become 7 over 3 here. So let's see if I can pull it all together. So first we have this 3 square root of 2 over 8 in front. This thing we're going to replace with this right here. So we have natural log 2 square root of 3 plus square root of 7. I'm going to break, for this square root of 7 over 3, I'll write it this way, and we'll write it as square root of 7 over square root of 3. For this piece here, we have this 2 square root of 3 in front. Let me get this out of the way because we're just going to use the square root of 7 square root of 3. Now let's just see if we can clean this up a little bit. I want to get this like MIT's solution, so I'll multiply in by 1 square root of 2 over square root of 2. So then doing that, we're going to have 2 times 3 over 8 square root of 2 here. Let's write this a little bit different. We've got a common denominator, so I'll write it as natural log square root of 7 plus 2 over square root of 3. And then for this part, this is just going to be 2 square root of 7. Square root of 3 times square root of 3 is just going to be a 3. But I can cancel 2 with 8, and we can get a 4 here. Distribute everything in, so we're going to have, now it's going to become 3 over 4 square root of 2 times this natural log piece. Then multiply 3 over 4 square root of 2 times this. The 3's are going to cancel. We have 2 square root of 7, and then we'll just have left, and then with this 3 gone, we just have 4 over square root of 2. I can cancel 2 with 4 here, and this becomes a 2. I'll make a little space right here. And so for my final solution, we have just 3 over 4 square root of 2 natural log square root of 7 plus 2 over square root of 3 plus square root of 7 over 2 square root of 2, and that's it. Okay, so as you can see, it was kind of a lot of work, especially this end part. Like this end part doing the trig substitution took a long time. Now, of course, with something like that, it was pretty straightforward, so you could probably use some formulas to speed it up. But no matter how you did it, I think it'd be really difficult in 4 minutes. Even if you used a formula, just kind of plugging in the boundaries at the end seems like it took some time. So I don't know. Let me know how you did it in the comments. Thanks so much for watching. Have a good day.